Hello everyone, myself Dr. Bismin Sherif, Assistant Professor, Department of Computer Applications, MES College, Marampally. Today we are going to having some discussion on the topic compiler design, and this is the way in which how I'm going to presenting this topic before you. We will start with why we need a compiler, then we will discuss the formal definition for the compiler, and finally we will end up with how this compilation happens. So before moving to the formal definition for the compiler, let us consider a real-world scenario. Suppose we have two persons, Alice and Bob, and Alice knows only German and Bob knows only English. So the communication between these two persons will not be quite easy, right? Because Alice knows only German, and as I have already mentioned, Bob knows only English. So how we can solve this situation? Yeah, definitely. We can have some language translator, and this lady, she is capable enough to capture what is Ali said in German and translate it into its equivalent in English, which is understood by the Bob. So, with the help of this language translator, we can solve this situation. Similarly, when it comes in the case of computer, the hardware part of the computer knows only the sequences of zeros and ones, as you know. Uh, there is machine code, right? But it's very difficult for the programmer, for us, or for the human beings to remember all these sequences of zeros and ones. So it's pretty fine for us to use some high-level programming languages to coding for the coding, right? But the problem is, even though we are writing the code in some high-level language, the hardware part knows only machine code. So we need to have some translator, some language translator, which is capable enough to convert this source code into its equivalent machine code, right? And here the compiler help us for this purpose. So here the compiler, this is capable enough to take this program, which is written in high-level language, and convert it into its machine code. So now we are moving to the formal definition for the compiler. Compiler, as we can say, it's a program which is capable enough to read a program in some high-level language, or we can call it as a source program, and it will translate the source program into its equivalent target program, right? And this target program, as you know, we can run this target program. We can give input to this target program, and the corresponding output will be generated. And during this compilation process, the compiler will report any errors. If any errors are present in the program, the compiler will detect it, and those kind of errors will also be reported, right? So that's the formal definition for the compiler. Compiler is actually a program that is capable enough to read a source program in some high-level language and translate it into its equivalent machine language. And during this translation, if any kind of error is present in your program, those errors will be reported, right? So uh, this now we are going to discuss about different phases of the compiler, or how this compilation happens. So for that we are actually going to open this yellow box, right? When we are going to open this yellow box, we can see have all these different steps is involved in this compilation process. So now we will focus on how this compilation happens, or how the compiler is capable enough to convert this source program into its target program. And for this it actually uses all these phases. Okay, so we have lexical analyzer phase, we have syntax analyzer, semantic analyzer, intermediate code generator, code optimizer, target code generator, and along with we have two supporting blocks like symbol table and error handling. So what we are gonna doing next is we will take any arbitrary statement from any programming language or any program you can take. Here I am just taking one statement, position equal to initial plus rate into 60, and we will explain what happens when this statement passes through each of these phases of the compilation process. Okay, and so you will get an idea about what is this compilation, or how this compilation basically happens. So our statement is position equal to initial plus rate into 60. You guys no need to worry about what is this position, what is this initial, what is this rate, or why is get multiplied with 60, or what is the relevance of this statement, or which program contains this statement. You guys no need to worry about any kind of those kind of steps. We are just taking any arbitrary statement, and we will discuss about what it happens to what this happen? What is happened to this statement when it passes through each phase of the compilation? Okay. So our statement is position equal to initial plus rate into 60, and it passes to the first phase of the compilation process, and that's lexical analyzer. It's also called a scanner. So when this statement passes to the first phase of the compilation process, okay, that is lexical analyzer. This lexical analyzer will identify different tokens present in this program or in this statement. So that is the basic functionality of this lexical analyzer. It will analyze the source program and it will identify what are the different tokens present in this program. So we know that this position, it's an identifier. So the token ID will be generated corresponding to this position. Then for this the equal to token will itself will be generated. For the next thing, that is initial, the corresponding token will be again, it's an identifier, so the token ID2 will be generated corresponding to this initial. For this plus, again, a plus token will be generated. For the next term, that is rate, it's again an identifier. So ID3, the token ID3 will be generated. For this into, the token into will be generated. And for the 60, the number token 60 will be generated. So this ID1 is nothing but it's an identifier. It's a first identifier. It is mentioned like ID1. Okay. And definitely you guys will step with how this lexical analyzer is capable enough to detect this position as identifier. Why don't it get stuck at this POS, or why don't it recognize POS only as an identifier, all those kind of things. But you will get more details about those kind of stuff when you dig deep into this lexical analysis space. As of now, you need not to worry about how basically this happens. We are actually using some of the concepts of finite automata and this regular expressions to recognize this token by this lexical analyzer. So, for as a beginner, you don't need to get stuck into those kind of things. At this moment, at this point of time, you guys need to remember only the basic function of this lexical analyzer is to recognize or identify the different tokens present in the program, and it will generate this sequence of tokens. Okay, fine. And now these tokens will be passed to the next phase of the compilation process, that is syntax analyzer. Syntax analyzer is also called as parser. Okay, and as the name suggests, the main functionality of this phase is to check whether the syntax of the program is correct or not. That's why it's called a syntax analyzer. And I will check whether the syntax of the program is correct or not. Syntax of the program is correct or not. And for checking whether the syntax is correct or not, it is actually constructing a parse tree, a tree-like structure. And with the help of this, it's actually check whether this syntax is correct or not. And to be frank, when you dig into the deep of this phase, you will get a clear idea about how this tree actually helps to check whether the syntax is correct or not. And basically, we are using different parsing approaches like top-down parsing, bottom-up parsing to check whether the syntax is correct or not. Fine. And now the syntax tree that would be, or we can call it as parse tree, okay, and this will be given as input to the next phase of the compilation, that is semantic analyzer or semantic process. So the basic function of the semantic analyzer is to check whether the semantic or the meaning of the program is correct or not. And also it will take care of different type checking. If there is any type mismatch, it will report those kind of things. So all these kind of things will be handled by the semantic analyzer phase. Suppose in this example, our variable's position, initial array, suppose we have declared all these kind of things as float or real, and the 60 is number, right? So here we have an issue like type mismatch, because here when we are considering this operation ID3 into 60, here ID3 is actually real, declared as real, but 60 is an integer. So definitely here this is an integer into real multiplication, right? So that's a type mismatch will be recognized at this moment, right? So basically what compiler did is, if it's possible for the compiler to do certain kind of type conversion, it will perform those kind of conversions. For example, here it's not that much difficult for the compiler to convert the 60, the number 60, integer number 60, to the real 60.0. It's not that much difficult for the compiler to convert this. You can use some inbuilt functions like into real of 60 to convert the 60 to 60.0. So so now this id3 is a real variable and the 60.0 is also a real variable. So now the issue is resolved. And this is what we call as type conversion, right? Type conversion. But to be frank, it's not possible for the compiler to do this type conversion in all the contexts. Suppose if it's a plus 60, right? If a plus 60, this is a character and this is 60 is a number. So if the context is something like this, it's not possible for the compiler to convert or to do some type conversion in this context. So it will report it as error. But fortunately, in our example, here the compiler is capable enough to convert the 60 to 60.0 using the function into real, and that's actually depicted in the string. Okay, fine. So the semantic analyzer, the working or the main functionality of the semantic analyzer is to check whether the semantic or the meaning of the program is correct or not, and also it will take care of this type checking, type mismatch, type conversion, all this kind of things, right? So now this tree that would be given as input to the next phase of the compilation, that is intermediate code generate. Okay, so as the name suggests, this phase actually generates some intermediate code. Okay, and we have different forms of intermediate codes like 3-address code. It's normally notated like 3AC, 3-address code. We have another kind of things like syntax tree, postfix notation. All these are different kinds of 3-address code, and majority cases we are actually focusing on this 3-address code. 3-address code kind of intermediate code generator. 3-address code is nothing but it's an intermediate representation word. If you're considering any statement on this 3-address code, it will contain only maximum of 3 addresses. So that's why it's called as 3-address code, and it's a type of intermediate representation. Okay, and you will get a detailed idea about this intermediate representation, different kind of intermediate representation, what's a 3-address code, what are the different operations or the statement that is available with this 3-address code. All those kind of things will be clear when you have a detailed idea about, or when you dig into the deep of this intermediate code generation phase, right? So here what I'm trying to give you only a peripheral view of what happens when this statement, when it passes through the different phases of the compilation process, right? So the 3-address code generated corresponding to this syntax tree, you can see the 3-address code in this slide. So here the first operation is actually this into real of 60. So that is actually shown over here, into real of 60, and that is stored in this temp1. Temp1 is nothing but a temporary variable. It's a compiler generated temporary variable, which is generated by the compiler for its internal uses, right? So initially this into real of 60, that will be stored on this temp1, and now this node is actually temp1, and now we can multiply this temp1 into id3, and we can store it into the another compiler generated temporary variable temp2, and now this id2. Okay, right? Now this enter tree branch, we can call it as temp2, right? So this temp2 that can be added with this id2, that's actually shown over here, id2 plus temp2, and that can be get stored on this temp3. Now your final result id1. Okay, we can store this value of temp3 to this id1, and this is how the intermediate code corresponding to this position equal to initial plus straight into 60 will be generated. Okay, we have few more steps in this compilation process. Those kind of explanation, the explanation for those phases will be, you can watch it on the next part. Thank you.